Okay, I suggest you start by pausing the video and reading through the question first and trying to work it out as far as you can get if you haven't already. I think it'll be more helpful in learning it and making sure you have it. Once you've done that, so this is what we're dealing with. We have 90 people, but it's actually divided into 45 pairs. So the first decision to make here would be, do we do a matched pairs t-test or a two-sample t-test? And of course, right here it already says matched pairs, so you probably know that this is a matched pairs. And it is indeed. The reason being, not just because we have 45 in each set, we have 45 with the close friends and 45 who did not have a close friend, but because there's a natural way of pairing them. If you give me anyone in the sample, I can naturally tell you who they would be paired with, which would be their twin. Of course, I did put a biological here. I think I meant identical. And there have been some really neat twin studies. This is not one of them. This is contrived data, and it would probably be pretty hard to get a sample the way that I've described it here. But for the sake of doing a matched pairs problem, that's what I created. So the first thing to do would be to match, even before you go through the steps of the test, would be to match up what our variables are. So our sample size in a matched pairs test is just the number of pairs. So if you're doing a pre-test, post-test, it would be the number of people who are taking a pre-test and post-test. In this case, even though we have 90 people, we have 45 pairs. So that's why n equals 45. X bar would be our sample mean, and S would be our sample standard deviation. Step one is hypothesis. So we're doing a matched pairs, which means we just have a single mean. And why do we have a single mean? It's because every pair of twins has one data value. So the way we did it was the close friend twin score minus the one who didn't have any close friends. So we have each of their scores on that self-esteem test, but we just create one difference. So if you score you were the one with the close friend and you scored a 8 on this test, and your sibling, your twin, biological twin, was the one without friends and they scored a 6, the difference score for you would be 2. For your pair, your twin pair would be 2, because you would take your score of 8 minus 6 for your twin. So we only end up having one mean, one standard deviation, one of everything basically. And that null hypothesis mean would be that the mean is 0. Why is that? Because if the twins are the same in terms of self-esteem, we would expect there to be no difference between them. So the average difference score would be 0. Now notice that we have the research question of whether or not the close friends had significantly higher self-esteem. This would be a case where we probably suspect either there'd be no difference or the ones with close friends might have higher self-esteem. And that would be a one-tailed or one-sided test, because we're specifically looking for higher, not just different in one way or the other. Once we get that, we go on to our critical value. So there's where that sample size of 45, remember our sample size of 45, we subtract 1 from that for the one sample t-test. And by the way, I'm saying one sample and matched pairs are the exact same statistically. Even though the setup's a little different, once you get down to the 5 steps, it's exactly identical, which is why I'll probably call it a one sample t-test. We have our alpha level. Looking this up on the chart, so degrees of freedom, we look for 44 and we don't find it. The closest, we have a 40 and we have a 50. Let's actually take a look down there. So if we go down, you see we have a 40 and we have a 50, but we don't have a 44. So what we do in that case, if it doesn't have our exact degrees of freedom, we go up the chart, so to the next lowest sample. So if we don't have 44, we go up to this 40 row. And then over here we have a one-sided, and our p-value is 0.05. So we're going to go up here until we get to the 40, and we get 1.684. So that's where we get this critical t-value of 1.684. And before you go drawing it like this, keep in mind that this would be for a two-tailed. If we had 1.6 is the critical. That would be what a two-tailed looked like, but in this case we just have one tail. It's a one-tailed test, so we set that cutoff at 1.684. If our t-statistic ends up being higher than 1.684, we're going to reject. Now we go down to step 3 to calculate the t-statistic. Here's one that you do need to pay close attention to the formulas. So these are the formulas you'll have on the test. The two-sample t-test and confidence interval are completely ready for you. This one needs some adjustment. So this was the original z-score formula. But when we're dealing with a standard deviation for a mean, for a sample mean, we need to use this right here from the central limit theorem. So this is what goes underneath here for the z-test if we're working with sample means. Now, because we're working with the t-test, we need to make one more little substitution. Since we don't know sigma, we replace that with s. So that ends up giving us this formula right here. So we have the difference between the sample mean and the null hypothesis mean divided by the standard error down there. And if you plug in the values that we had early on up there, you'll end up getting about 6.05. And if we plot that on our distribution here, we'll see that our sample is way up here in the rejection region. So we're well past that critical value. So in step 4, because we are in the rejection region, we do reject the null hypothesis. So going back, what was our null hypothesis? Our null hypothesis was the mean is 0. What does that mean? This means that there was no difference between the twins. We reject that idea. We reject the idea that there's no difference. In other words, we have found evidence of a difference. So our evidence suggests that the twins with at least one close friends do have higher self-esteem than their twin without any close friends. We haven't proved it, but by rejecting the null hypothesis, we've tentatively concluded for our alternative hypothesis, which was that there was more self-esteem, higher self-esteem in the twin that had the close friend versus the one without any close friends. And notice what we're doing here. This is now talking about the population of all twins, at least the ones that would be in that situation, having one with the elementary close friend and one without. We're going beyond our sample now. So this was the original sample values, but now we're going beyond. Even in the population, we think that there's a significant difference. Of course, this is statistical significance. We'd want to take a closer look to see if this was a practically significant difference too, to see what the effect size, and if it was just a tiny little bit, or if it was a substantial, meaningful effect that this having a close friend has. One final thing to mention here, is it possible we made an error? When we made our decision on the null hypothesis and our conclusion, is it possible we made an error? Yes, always. In null hypothesis testing, it's always possible that you made an error. If we made an error, which error would we have made? Well, because we rejected the null hypothesis, it's possible that we rejected the null hypothesis even though the null hypothesis was true. So if that's the case, we made a type 1 error. That's the definition of a type 1 error.